Good afternoon, everyone. Pleasure to join you today. I'm going to talk from a transmission owner's perspective, owner and operator, to kind of give an idea of the challenges that we're facing. Some that are emerging and some that are related to emergency response. And some of these topics were already addressed by some of the presenters. So it's heartening to see that researchers are taking into account the interoperability and things of that nature with respect to grid support. I'm with American Transmission Company. We own and operate the majority of the grid in Wisconsin, Upper Peninsula of Michigan, and parts of Minnesota and Illinois. And we are looking to expand our footprint to some degree. Some of the emerging challenges that we're facing as a transmission-only company have to do with supporting a changing resource mix on the generation side of the business. There's, of course, a very strong move toward reduction of baseload generation. Some of the consequences of that reduced baseload generation have to do with system operations, particularly system inertia impacts. As fewer and fewer baseload units are available on the system, we have less mechanical and electrical inertia as a result of that. Fault current may be reducing as well because one of the dynamics of a large prime mover connected to a large synchronous generator is a lot of available fault current, which of course then makes coordination of relaying potentially a problem. Also accompanying that is a possible dynamic VAR reduction in a specific area. So that happens to obviously reduce our ability to support voltages in an area and prevent voltage collapse. Now, none of these things have happened to a large degree, but we're just looking out into the future, and these things are on our radar screen as possible effects of these changes. In addition to that, of course, when baseload generation goes away, we have to go to other generation platforms, and part of that is increased renewable penetration into our systems. Coming with that might be voltage harmonics as a result of using power electronics to interface with wind generation. System control may be a problem where we may have reduced ride-through capabilities for some generators that are hooked up to renewable generation systems. As we get more and more power electronics, there may be some difficulties with setting these up properly or maybe getting the ability to ride through an event. And there was a NERC event that took place, I think it was a year before last. It's called the Blue Cut event. I don't have all the details, but basically what happened was some, I think it was solar generation, basically got disconnected from the grid because of poor ride-through settings on their power electronics. Also, another challenge we have is aggregating many different types of resources. It's a lot easier to work with a few large generators than it is to try to interface with and control and also dispatch a number of smaller units, whether it be distributed generation or renewable resources that attach to distribution systems, or maybe even grid scale energy, renewable energy portfolios. And therefore, as a result of that, we may have some struggles matching demand to generation in real time. Some of the things that were talked about by some of the researchers on the call today had to do with modeling systems for planning dynamic studies as well as load profiles. It's really hard for us at times to figure out what the mix of the loads are on our system and try to adequately model those appropriately so that we get the right dynamic responses that would basically model what's really going to go on when we have a system event. And then, of course, dispatch predictability is a difficult thing and maybe an area where some research could be done to maybe help gain an understanding of renewable resource availability in day-ahead markets. There are some emergency challenges as well, having to do with resiliency responses. Some of these were spoken about. We have physical security systems for protecting our assets out in the field. We harden our control houses against physical attacks and weather events. We're looking into EMP hardening and GMD responses for geomagnetic disturbances on our system to try to prevent wholesale power loss during such extreme events. We also are adding detection systems to our system, such as cameras for intelligence and multifunction purposes out in the field for intelligence gathering at substations and maybe even on transmission lines. Some utilities are deploying shot sensors when there's physical attacks underway to try to get a triangulate on where the shots are coming from, and perimeter monitors, whether it be tripwire devices, vibration sensing, or perimeter cameras that could give us some intelligence as to intrusion threats. We also have large cybersecurity teams that are always looking at preventing cyber attacks and mitigating the effects of attacks, and also mitigating the critical infrastructure interdependency risks for high impact, low frequency kinds of threats, like large-scale hurricanes or wind events or ice storms or things of that nature. So we notice that there are interdependencies between natural gas supply, water supply, communications, and other support systems that might have an impact during what we might call a black or a dark sky event. More emergency challenges, recovery. What happens if we do have a dark sky event and we go dark on our EMS systems? Are there more resilient systems out there that could maybe live through more high impact, low frequency type events? Are there cyber-resistant SCADA systems that we could deploy? What about backup SCADA, where we might have a few telemetry points that are more robust and resilient that could give us an idea of what the rest of the system is doing from a few data points as opposed to thousands of data points? Emergency voice and data communications are beginning to be studied. What kinds of systems can we deploy that might be able to be backups to the traditional cell phone systems and other communication systems that probably would not be available during a dark sky event? Black start resources, availability, control, visibility to many smaller units. How are we going to interface with our black start resources to make sure we get back on in a reasonable amount of time? Some are starting to propose using energy storage platforms for black start capabilities, and we're starting to kind of look into that a little bit at ATC as well. Some of the complications with that are fault current availability. Again, how do you size the units to start a motor or a generator or some kind of support system miles away from the black start resource? Then microgrids during recovery, how will they perform? What about fuel supplies to them? What about situational awareness with respect to their availability? So that is all I have for my presentation. Thank you very much.